Welcome to G Fun Facts Online. Today we are diving straight into one of the most profound astronomical events of our time. In the summer of 2025, the global astronomical community was galvanized by the arrival of a true cosmic outsider. When an object from the space between the stars pierces the veil of our solar system, it carries with it the pristine secrets of an alien genesis. This is the story of 3I/Atlas, only the third confirmed interstellar object to ever enter our celestial neighborhood. But what makes 3I/Atlas truly historic is not just its arrival, but what it brought with it. Packed with an astonishingly high concentration of methanol, 3I/Atlas is essentially a floating, frozen reservoir of alcohol, and it tells a vivid story of a distant, frigid stellar nursery located far beyond the reach of our own sun. Let us unpack the monumental leap in astrochemistry brought about by this interstellar vagabond. Interstellar objects are the ultimate cosmic wanderers. For decades, scientists theorized that the space between the stars must be littered with ejected planetary building blocks. These would be comets and asteroids, violently thrown out of their home systems by the gravitational bullying of giant planets during the chaotic early days of planetary formation. Yet, it was not until 2017, with the discovery of the cigar-shaped Oumuamua, followed by the rogue comet Borisov in 2019, that humanity finally laid eyes on these travelers. The third confirmed visitor, 3I/Atlas, was first spotted on July 1, 2025. It was detected by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, a survey telescope located in Rio Hurtado, Chile. ATLAS is primarily an automated system designed to monitor the skies for near-Earth asteroids that might pose an impact threat. However, its wide-field surveillance makes it uniquely suited for catching fast-moving anomalies. When orbital dynamicists analyzed the data, they realized this newly discovered comet, officially designated C/2025N1, was moving on a strongly hyperbolic trajectory. In orbital mechanics, a closed elliptical orbit bound to our Sun has an eccentricity of less than 1. Oumuamua had an eccentricity of 1.2, and Borisov had 3.4. 3I/Atlas, however, possessed an extreme orbital eccentricity of 6.141. When traced mathematically backwards in time, it was undeniable that 3I/Atlas originated from elsewhere in the Milky Way. Plunging through our solar system in a nearly straight line, the comet traveled at a blistering speed of over 60 kilometers per second, which is about 216,000 kilometers per hour. To make things even more complex, it approached on a retrograde path, moving in the exact opposite direction to the standard orbital flow of the planets in our solar system. Because of this immense velocity and deep trajectory, a rendezvous mission was physically impossible. By the time it was confirmed, the launch window for even a fleeting flyby probe had closed. But humanity was not unprepared. If interstellar objects are cosmic celebrities, 3I/Atlas received the ultimate red carpet treatment. Over the course of its passage, it was photographed by at least 16 different scientific spacecraft. As the comet plunged toward its closest approach to the Sun, known as perihelion, on October 29, 2025, a vast array of instruments turned their mechanical eyes toward it. Ground-based observatories relentlessly monitored it, submitting over 4,000 astrometric observations. Space-based telescopes provided dramatic insights. NASA's Hubble Space Telescope and the James Webb Space Telescope locked onto the comet. The newly launched Spherix Observatory, mapping the sky in near-infrared, utilized the comet as a prime target of opportunity, documenting its sudden awakening as it shed its ancient, cosmic ray-battered crust. The entire solar system became an observatory. NASA's Lucy mission spotted it from 240 million miles away, while en route to Jupiter's Trojan asteroids. Solar observation spacecraft, like SOHO, Stereo, and Punch, tracked its brilliant tail braving intense solar radiation. Even from Mars, the Mars Reconnaissance Orbiter, MAVEN, and the Perseverance rover pointed their cameras to the night sky. Perhaps the most remarkable images came from the European Space Agency's Jupiter Icy Moons Explorer, or JUICE. En route to the outer solar system, JUICE used its high-gain antenna as a heat shield against the Sun while operating its Janus science camera. Just a week after the comet's perihelion, JUICE captured over 120 images from a distance of 66 million kilometers. These images revealed a bright halo of gas, a long tail, dynamic rays, jet streams, and structural filaments. Through this coordinated, solar system-wide campaign, astronomers were prepared to dissect the chemical composition of 3I/Atlas. What they found shattered existing paradigms of comet chemistry. Most native comets are composed of water ice, carbon dioxide, carbon monoxide, and trace organics. When they approach the Sun, solar heat causes these ices to sublimate directly from solid to gas. 3I/Atlas initially displayed delayed activity because its surface had been heavily irradiated by galactic cosmic rays for eons, creating a hardened shell. But as it reached a minimum distance of 1.36 astronomical units, just inside the orbit of Mars, the stellar heat cracked this ancient crust. Early James Webb observations showed the coma was heavily dominated by carbon dioxide, rather than water vapor typical of local comets. It also exhibited emissions of hydrogen cyanide and atomic nickel. But the true shock came from the Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile. Using ALMA's Atacama Compact Array, a team led by Dr. Nathan Roth of American University effectively took a chemical fingerprint of the star system where 3I/Atlas was born. ALMA is uniquely capable of detecting faint submillimeter radio frequencies emitted by rotating molecules. The data revealed that 3I/Atlas was packed with an extraordinarily high amount of methanol. Methanol is an organic alcohol tied closely to prebiotic chemistry. While found in solar system comets, the sheer volume pouring out of 3I/Atlas was unprecedented. The researchers compared the production rate of methanol to hydrogen cyanide, a standard baseline for cometary chemistry. In mid-September 2025, they measured staggering methanol to hydrogen cyanide ratios of roughly 79:1 and 124:1. These values represent an enrichment nearly 2 orders of magnitude higher than comets originating from our own Oort cloud or Kuiper belt. In recorded history, these heavily enriched values are surpassed only by one highly anomalous native comet, C/2016 R2. Beyond identifying the chemical inventory, ALMA's high-resolution imaging allowed astronomers to map exactly how these alien molecules behaved in the vacuum of space. The outgassing behaviors of hydrogen cyanide and methanol were distinctly different. Hydrogen cyanide was sublimating directly from the comet's central solid nucleus. Its production rate was steady, concentrated primarily in the sunward hemisphere where solar heating was most intense. This is standard behavior for volatile organics, locked deep within the primary ice matrix. Methanol, however, displayed a far more complex escape pattern. Instead of solely erupting from the main nucleus, the methanol was being released from a vast cloud of icy dust grains suspended within the coma itself. As 3I/Atlas approached the Sun, these tiny ejected particles acted like miniature comets. As the microscopic grains absorbed sunlight, their internal ices rapidly turned into gas, saturating the surrounding space with methanol. This distributed source phenomenon has been witnessed in a select few local comets, but seeing the detailed physics in an interstellar object was a historic first. Why does this methanol to hydrogen cyanide ratio matter so much? In astrochemistry, comets are the frozen time capsules of planetary formation. They are the pristine, unaltered leftovers from the protoplanetary disk of gas and dust that eventually coalesces into planets. Because 3I/Atlas formed around a completely different star, its chemistry allows us to reverse engineer an alien stellar nursery. The extreme abundance of methanol strongly indicates the icy material formed under conditions drastically different from our solar system. Methanol is predominantly formed in space on the surfaces of microscopic dust grains. In the deep freeze of a protoplanetary disk, carbon monoxide gas freezes onto these grains. With the right amount of cosmic radiation or stellar ultraviolet light, hydrogen atoms sequentially attach to the frozen carbon monoxide, gradually hydrogenating it into formaldehyde and eventually methanol. For 3I/Atlas to contain such a massive reservoir of alcohol, it likely aggregated in a specific region of its native disk known as the carbon monoxide snowline. This is the precise distance from the host star where temperatures drop low enough, around -250 degrees Celsius, for carbon monoxide to freeze solid. This extreme enrichment suggests an environment with unique temperature gradients or different radiation processing compared to the ancient solar nebula that birthed Earth. Furthermore, the abundance of methanol has profound implications for prebiotic chemistry and other star systems. Methanol is a complex organic molecule that serves as a crucial chemical precursor for the synthesis of life-essential compounds, including amino acids and sugars. Finding a randomly intercepted chunk of interstellar ice, so deeply saturated with a prebiotic building block, acts as a compelling indicator that the chemical prerequisites for life are abundantly manufactured in planetary systems far beyond our own. Following its closest approach to the Sun in late October 2025, 3I Atlas began its long, unyielding journey back into the frigid abyss. By December 2025, it moved safely past Earth at a distance of 170 million miles, re-emerging from the Sun's glare for a final round of observations before fading into the cosmic dark. Moving at its hyperbolic velocity, it will eventually escape the gravitational pull of our Sun entirely, never to return. We may never know the specific star that birthed 3I/Atlas. It could be older than our own Sun, having wandered the lonely voids for billions of years before its brief, fiery encounter with us. Yet its legacy is permanently etched into the annals of astronomy. Before Oumuamua, Borisov, and Atlas, studying exoplanetary systems meant analyzing dimming starlight or subtle gravitational wobbles. Comet 3I/Atlas shattered this barrier, offering a high-fidelity physical sample of a distant world's building blocks. It proved the universe is connected by wandering envoys of ice and dust. As we build more advanced sky surveys like the Vera C. Rubin Observatory, we anticipate finding these visitors with increasing frequency. But 3I/Atlas will forever hold a unique place in history, as the celestial wanderer bursting with alcohol, which generously allowed the telescopes of Earth to take a chemical fingerprint of the wider galaxy. Through the lenses of ALMA, the James Webb Space Telescope, and an armada of interplanetary spacecraft, we did not just look out into the cosmos. For a brief, shining moment, the cosmos brought a piece of itself directly to us. Thank you for joining us on G Fun Facts Online. Keep looking up and keep wondering about the infinite mysteries waiting just beyond the stars.